Chapter 6. Special Control Valves.
Next, we turn to high and low flow valves.
In this chapter, I would like to introduce special applications that are difficult to handle with standard control valves and the valve modifications tailored for them. The standard control valves we covered in previous chapters can handle a very wide range of control applications. To define that standard range quantitatively, pressure ranges from atmospheric pressure up to 6,000 sig, or 414 bar, and temperature ranges from -150 degrees Fahrenheit -101 degrees Celsius to 450 degrees Fahrenheit 232 degrees Celsius. The flow coefficient CV ranges from 1.0 to 25,000, with additional limits imposed by general industrial standards. However, even within these standard applications, several factors such as fluid corrosion, viscosity, and allowable leakage rates must be considered. And the further an application falls outside these standard limits, the more careful judgment is required in valve selection.
I would like to introduce high-capacity control valves. Generally, globe-style valves larger than 12 inches, ball valves over 24 inches, and high-performance butterfly valves larger than 48 inches fall into the special valve category. When valve size increases arithmetically, static pressure loads at shutoff increase geometrically. As a result, shaft strength, bearing loads, unbalanced forces, and the required actuator thrust all become more significant as the valve size increases. Therefore, for large valves, the maximum allowable pressure drop is usually reduced to keep design and actuator requirements within reasonable limits. However, even with these lowered working pressure ratings, the flow capacity of some large flow valves remains tremendous.
In large flow installations, noise levels must be carefully considered because sound pressure levels increase in direct proportion to flow magnitude. To keep valve-originated noise within tolerable limits, large cast or fabricated valve body designs have been developed, as shown in Figure 6.1. These bodies normally use a cage-style construction, incorporating unusually long plug travel, a great number of small flow openings through the cage wall, and an expanded outlet line connection. This minimizes noise output and reduces fluid velocity. Naturally, actuator requirements become more severe, so long-stroke, double-acting pneumatic pistons are typically specified for large flow applications.
This shows the appearance and structure of a large flow valve body optimized for noise attenuation service.
The physical size and weight of large valves and actuator components complicate installation and maintenance procedures. Heavy-duty hoists are required to install the valve body assembly into the pipeline, or to remove and replace major trim parts. Additionally, maintenance personnel must closely follow the manufacturer's instruction manuals to minimize the risk of injury. Next, I will introduce low-flow control valves. There are many applications in laboratories and pilot plants, as well as in general processing industries, where extremely low flow rates must be controlled. These are typically handled in one of two ways. The first is applying special trims to standard control valve bodies. These special trims consist of a seat ring and plug designed and machined to very close tolerances to allow accurate control of very small flows.
These types of special trim constructions can often handle CV values as low as 0.03. Using special trims in standard control valves is economical because it reduces the need for spare parts inventory for special valves and actuators. This approach also makes future flow expansions easy, as you only need to replace the trim components within the standard control valve body. Meanwhile, as shown in Figure 6.2, control valves specifically designed for very low flow rates also handle these applications. These dedicated valves can handle even lower CV ranges.
This is a special valve designed to enable precise control even within very low flow ranges.
Next, we turn to temp and cryogenic valves.
The specialty control valves mentioned earlier handle very low flow rates, down to a CV of 0.00001, or 1 millionth. These specialty control valves are compact and lightweight because they are often used in laboratory environments where very light schedule piping and tubing are used. These valves are specially designed for the accurate control of very low-flowing liquid or gaseous fluid applications. Next, I will introduce high-temperature control valves. Control valves used at temperatures exceeding 450 degrees Fahrenheit 232 degrees Celsius must be designed and specified with those temperature conditions in mind. In high-temperature environments, such as those encountered in boiler feedwater systems or superheater bypass systems, standard materials may not be sufficient.
I would like to discuss material selection for high-temperature control valves. For services exceeding 450 degrees Fahrenheit 232 degrees Celsius, the valve must be designed and specified from the start based on the temperature conditions. Typical applications include areas subject to high temperatures, such as boiler feedwater systems and superheater bypass systems. At these temperatures, the materials used in standard control valves are inadequate. Plastics, elastomers, and standard gaskets cannot withstand these conditions and must be replaced with more durable materials. Metal-to-metal seating is always used for the seat, and semi-metallic or laminated flexible graphite materials are used for packing. For gaskets, a combination of spiral wound stainless steel and flexible graphite is required. Regarding the valve body material, CRMO steel castings are frequently used for temperatures exceeding 1000 degrees Fahrenheit 538 degrees Celsius. ASTM A217 grade WC9 is used up to 1100 degrees Fahrenheit 593 degrees Celsius, and up to 1500 degrees Fahrenheit 816 degrees Celsius. ASTM A351 grade CF8M, or Type 316 stainless steel, is typically selected.
I will now cover valve body materials for ultra-high temperatures and move on to cryogenic service. For the range between 1000 degrees Fahrenheit 538 degrees Celsius and 1500 degrees Fahrenheit 816 degrees Celsius, the carbon content must be managed at the upper end of the range, between 0.04 and 0.08%. In higher temperature regions, 9% Cr, 1% Mo, and vanadium materials are used. ASTM A217 grade C12A castings and ASTM A182 grade F91 forgings are used at temperatures up to 1200 degrees Fahrenheit 650 degrees Celsius. Extension bonnets protect packing box parts from extremely high temperatures. Typical trim materials include cobalt-based alloy 6, type 316 with alloy 6 hard-facing, and nitride type 422 stainless steel. Now, let's move on to cryogenic service. Cryogenics is the science dealing with materials and processes at temperatures below minus 150 degrees Fahrenheit minus 101 degrees Celsius. In cryogenic control valves, issues quite similar to those of high-temperature valves must be considered. Plastic and elastomeric components often cease to function properly at temperatures below 0 degrees Fahrenheit minus 18 degrees Celsius.
I will now discuss the issues that arise with packing and plug seals in cryogenic regions. In these low-temperature ranges, components such as packing and plug seals require special consideration. In the case of plug seals, standard soft seals become very hard and lose flexibility as the temperature drops. Consequently, they fail to provide the shut-off performance expected from a soft seat. In other words, the sealing effect intended for a soft seat is lost. To solve this problem, special elastomers have been applied in this temperature range, although separate loading is required to achieve a tight seal. This loading will be covered in the following explanation.
I will now explain how to prevent icing using extension bonnets. The special elastomers mentioned earlier require separate loading, or pressurization, to achieve a tight seal. Packing becomes an issue in cryogenic applications because of the frost that forms on the valves. Moisture from the atmosphere condenses on colder surfaces, and if the surface temperature is below freezing, that moisture freezes into a layer of frost. When this frost and ice form on the bonnet and stem areas of control valves and the actuator strokes the stem, the frost layer on the stem is drawn into the packing, tearing it and resulting in a loss of seal. The solution is to use extension bonnets. As shown in Figure 6.3, using an extension bonnet keeps the packing box area of the control valve warmed by ambient temperatures, thereby preventing frost from forming on the stem and packing box areas.
This is a typical extension bonnet designed for thermal insulation or to secure installation space.
I would like to introduce the determination of extension bonnet length and customized characteristic trims. The length of the extension bonnet is determined by the application temperature and insulation requirements. The colder the application, the longer the extension bonnet required. For cryogenic applications, the construction materials are generally CF8M for the body and bonnet and 300 series stainless steel for the trim. In flashing applications, hard facing might be required to combat erosion. Next, I will discuss customized characteristic trims. The valve characteristics used in standard control valves, as shown in Figure 6.4, meet the requirements of most applications. However, custom characteristics are often needed for specific applications. In these instances, special trim designs can be manufactured to meet these requirements.
Next, we turn to valve characteristics.
This is the inherent characteristic graph, which shows the change in flow rate according to the valve travel.
I would like to introduce how to implement valve characteristics using contoured plugs and cages, as well as noise abatement. In the case of contoured plugs, the design of the plug tip can be modified so that the unobstructed flow area changes in size as the plug moves through its travel range. This allows for the generation of a specific flow characteristic. Likewise, cages can be redesigned to meet specific characteristics. This is especially common in noise abatement type trims, because in these trims, a high level of noise abatement may be required at low flow rates, but much lower abatement levels are required for higher flow rate conditions.
Next, we turn to nuclear service (STD).
I would like to introduce the regulatory framework under which control valves for nuclear power plants are manufactured. In the U.S., since 1970, manufacturers and suppliers of nuclear power plant components have been subject to the requirements of Appendix B of 10 CFR Part 50. The official name of this regulation is Quality Assurance Criteria for Nuclear Power Plants and Fuel Reprocessing Plants. The agency that enforces this regulation is the U.S. Nuclear Regulatory Commission, or NRC. An important point here is that the ultimate responsibility for proving compliance with Appendix B rests with the plant owner. Since the owner cannot manufacture everything themselves, they rely on documented evidence provided by various component manufacturers. This evidence must show that the components were manufactured, inspected, and tested by proven techniques, performed by qualified personnel according to documented procedures.
The medium that translates the federal regulation requirements mentioned earlier into actual valve specifications is the ASME Boiler and Pressure Vessel Code. Most nuclear power plant components are specified in accordance with Section 3 of this code, titled Nuclear Power Plant Components. Section 3 is applied to align with the requirements of the Code of Federal Regulations. All aspects of the manufacturing process must be documented in a quality control manual, and ASME must audit and certify this manual before the actual manufacture of the components. All subsequent manufacturing materials and operations are checked by an authorized inspector. All valves manufactured in accordance with Section 3 requirements receive an ASME code nameplate and an N stamp, which is the symbol of acceptability for service in nuclear power plant applications.
In practice, it is very important to distinguish what Section 3 covers and what it does not. First, the scope of non-application. It does not apply to parts not associated with the pressure retaining function, nor to actuators and accessories unless they are pressure retaining parts. It also does not apply to the deterioration of valve components due to radiation, corrosion, erosion, seismic or environmental qualifications, or to cleaning, painting, or packaging requirements. However, these excluded items are usually specified separately in customer specifications. Conversely, the scope of application includes materials used for pressure-retaining parts, design criteria, fabrication procedures, non-destructive test procedures for pressure-retaining parts, hydrostatic testing, and marking and stamping procedures. Finally, Section 3 is revised by semi-annual addenda, which may be used after the date of issue and become mandatory 6 months after the date of issue.
Next, we turn to SSC and NACE standards.
Now, I would like to introduce sulfide stress cracking, which is a problem in harsh environments containing hydrogen sulfide, so-called sour service. NACE International is a technical society concerned with corrosion and corrosion-related issues. NACE manages many standards, but by far the most influential and well-known is MR0, MR0175. The former name of this standard was Sulfide Stress Cracking Resistant Metallic Materials for Oilfield Equipment. MR0175 was issued in 1975 to provide guidelines for the selection of materials that are resistant to failure in hydrogen sulfide-containing oil and gas production environments. Because this standard has been so widely referenced, the term NACE has become nearly synonymous with MR0175 throughout the process industry. However, the situation changed in 2003. In the 2003 revision, the standard was significantly modified to cover chloride stress corrosion cracking in addition to sulfide stress cracking.
As I mentioned, the standard was expanded with the 2003 revision, and as a result, the standard system split into two branches. First, in late 2003, MR0175 was reformatted and released as a joint NACE/ISO document. This integrated document is NACE MR0175/ISO 15156, and it covers materials for use in H2S, containing environments in oil and gas production within the petroleum and natural gas industries. Meanwhile, in April 2003, NACE also released a separate new standard, MR0103. The title of this standard is Materials Resistant to Sulfide Stress Cracking in Corrosive Petroleum Refining Environments. Simply put, you can think of MR0103 as the NACE MR0175 for the refining industry. Thus, the standards diverged into two streams, MR0175/ISO 15156 for the production sector, and MR0103 for the refining sector.
I would like to introduce the nature of MR0103, the refining standard, and the extent to which these standards are legally mandated. MR0103 only addresses sulfide stress cracking, and in that respect, it is similar in many ways to the pre-2003 revisions of MR0175. The application of MR0103 in the refining industry is steadily increasing. Here, it is necessary to distinguish the level of mandate. In some states and regions in the USA, compliance with certain revisions of NACE MR0175 or MR0175/ISO 15156 is mandated by statute. On the other hand, at this time, MR0103 is not legally mandated by any governing bodies. Finally, the following explanation is based on the content and requirements of the pre-2003 MR0175, but it cannot be presented in as much detail as the actual standard, nor does it guarantee the suitability of specific materials. Therefore, I strongly recommend referring to the actual standard text before selecting control valves for sour service.
I will now explain how to select metallic materials that resist sulfide stress cracking, or SSC. Most ferrous metals become susceptible to sulfide stress cracking when hardened by heat treatment or cold work. Conversely, many ferrous metals can actually improve their resistance through proper heat treatment. Carbon and low-alloy steels must be properly heat-treated, and a maximum hardness limit of 22 HRC applies. Austenitic stainless steels have the best resistance in annealed condition, and in some specific grades and conditions, up to 35 HRC is acceptable. Copper-based alloys are inherently resistant, but due to concerns about general corrosion, they are generally not used in critical parts of a valve without the purchaser's approval. Nickel alloys generally provide the best resistance to sulfide stress cracking.
Next, I will introduce the sulfide stress cracking requirements regarding nickel alloys, plating, welding, and identification marking. Some precipitation hardenable nickel alloys can be used up to 40 HRC in applications requiring high strength or hardness. Plating such as chromium or nickel does not protect against sulfide stress cracking. Therefore, while its use is allowed in sour applications for wear resistance, it cannot be used to protect a non-resistant base material from SSC. Weld repairs and fabrication welds on carbon and low-alloy steels must be properly processed to ensure that the base metal, the heat-affected zone, HAZ, and the weld deposit all meet the maximum hardness requirement of 22 HRC or less. Post-weld heat treatment, or PWHT, is mandatory for alloy steels and is generally applied to carbon steels as well. For identification marking, conventional stamping is permissible in low-stress areas, such as on the outside diameter of line flanges.
I previously mentioned low-stress areas like the outer diameter of line flanges, but in other areas, low-stress identification stamping must be used. The standard precludes using ASTM A193 grade B7 bolting for applications that are considered exposed. Therefore, SSC-resistant bolting materials, such as ASTM A193 grade B7M, are used, but in this case, valves originally designed for B7 bolting may require derating. For example, in a Class 600 globe valve, 17-4 pH H1150 dBl bolting can be used to avoid derating.
Now, I would like to introduce the introduction and current usage of the NACE MR0175/ISO 15156 standard. This integrated standard brought significant changes to the previous standard. However, many end users continue to specify NACE MR0175-2002, as they feel this version is sufficient to provide a good service life. I will summarize the most significant changes of the new integrated standard in the following sections.
I'll introduce the major changes in MR0175/ISO 15156. First, 17-4 pH H1150 dBl bolting, which was previously used for full-rated exposed bolting in a Class 600 globe valve, is no longer allowed. Second, this revision addresses both sulfide stress cracking and chloride stress corrosion. Prior versions simply listed most materials as acceptable or unacceptable. However, as the scope expanded to cover chloride stress corrosion, the new standard changed to allow all corrosion-resistant alloys within certain limits, referred to as environmental limits or environmental restrictions. These environmental limits are typically expressed in terms of H2S partial pressure, maximum temperature, ppm chlorides, and the presence of free sulfur. Third, the use of 316 material is still allowed, but only under very limited environmental conditions. If strictly followed, this material will find very little use in practice.
Next, I'll discuss the scope of application and the division of responsibility for NACE MR0175 and ISO 15156. This standard applies to petroleum production, drilling, gathering, and flow line equipment, as well as field processing facilities, and is limited to H2S, bearing hydrocarbon service. Importantly, it does not apply to refineries, as the refinery environment is covered by a separate standard, MR0103. The division of responsibility is also clear. The buyer is responsible for specifying the correct materials, and the manufacturer is responsible for ensuring the specified materials meet the metallurgical requirements of MR0175 and ISO 15156. This revision defines the usage conditions for corrosion-resistant alloys through environmental limits, such as H2S partial pressure, maximum temperature, ppm chlorides, and the presence of free sulfur. Meanwhile, many end users still specify the 2002 edition of MR0175, believing that version alone is enough to ensure sufficient service life.
Following this, I'll introduce NACE MR0103, the sulfide stress cracking standard for the refining industry. This standard is similar in many respects to the MR0175 revisions prior to 2003, but there are a few important differences. First, the definition of what constitutes a sour environment, that is, a corrosive environment, is different, as MR0103 uses a refinery-based definition. Also, the responsibility for determining and imposing when the requirements of this standard apply lies with the user. The biggest difference is the scope. While the 2002 and earlier revisions of MR0175 placed environmental restrictions on some materials, MR0103 deals only with sulfide stress cracking and does not impose environmental limits on any materials. Therefore, materials are categorized as either acceptable or not. Finally, carbon steel-based materials classified as P-No. 1, Group 1 or Group 2 in the ASME boiler and pressure vessel code are acceptable per MR0103 without base metal hardness requirements.
Now, I'll introduce the range of carbon steel-based materials to which the NACE MR0103 standard applies. Carbon steels classified as P-No. 1. Group 1 and 2 in the ASME boiler and pressure vessel code are recognized as satisfying MR0103 without separate base metal hardness requirements. Specifically, Pino. Group 1 and 2 include WCC and LCC castings, A105 forgings, A516 grade 70 plate, and other common carbon steel pressure vessel materials. These materials are representative carbon steels commonly used in refinery environments.
Next, I would like to introduce the welding control requirements that MR0103 imposes on carbon steels. MR0103 requires more rigorous welding controls for carbon steels than those in the 2022 edition of MR0175. Specifically, it stipulates that Pino 1 carbon steels must be welded according to another NACE document called RP0472. This RP0472 document contains methods and controls to prevent in-service environmental cracking of carbon steel weldments in corrosive petroleum refining environments. This regulation ensures that both the weld deposit and the heat-affected zone, or HAZ, are soft enough to resist sulfide stress cracking. Additionally, RP0472 requires actual hardness testing of weld deposits during production, although this hardness testing may be waived if certain welding process and filler material combinations are employed.
Now, I will explain how the hardness of the weld heat-affected zone is controlled in the NACE MR0103 standard. The hardness of the heat-affected zone, or HAZ, around the weld can be managed in 2 primary ways. The first is by applying post-weld heat treatment, known as PWHD, and the second is by restricting the chemistry of the base material itself. A representative example of restricting chemical composition is imposing a maximum carbon equivalent, or CE value, below a certain level. The reason for controlling hardness in this way is to prevent stress cracking occurring in corrosion environments.
Next, I will discuss the restrictions regarding bolting materials. The MR0103 standard does not allow the use of S17400 H1150 material for bolting. This is the same policy as the MR0175 standard revised after 2000. In the past, 17-4 pH H1150 DBL bolting was widely used for full-rated exposed bolting in Class 600 valves. However, please note that due to this specification change, bolting of this material is no longer permitted.